everyone. Welcome to the second talk. This is Srijit from yesterday, Srijit told us about how you can study various systems by putting them in a box. Today he's here to tell us about more details about the process, and in particular, he will tell us about probing the QCD spectrum and its implications from first principles. So,
yes.
Looking forward to this.
Yes. Yeah, thanks Prasad. Thanks. So you see me for another afternoon today. I'm giving a talk about, you can think of this as a more focused talk from yesterday. Yesterday it was a broad topic where I discussed the whole finite volume effects and the things one can do with connecting finite volume to infinite volume and how ubiquitous it is in studying physics. So today I'm going to discuss how can we probe the QCD spectrum using finite volume effects and then study how it can affect other observables from first principles. So this is the outline of my talk. I will introduce the topic and talk about QCD spectrum and why do we need to study them, and talk about the lattice method briefly, and then the formalism and the details of performing a full-fledged lattice calculation, and then what are the implications of this lattice calculation for instance the G-2 hadronic contributions and the future avenues of research. Okay, let's start. So different gapped spectra that we all have come across throughout our careers, starting from undergraduate to PhD and postdoc. When you start off as an undergraduate, you come across the harmonic oscillator, and then you go about doing the hydrogen atom. So, and then, at least in my PhD and postdoc, I came across this QCD spectrum that I also flashed yesterday. And you can see how the complexity of the systems have changed. As what you had previously, you have two particles with just a harmonic oscillator potential between them. And then you go on to do QED. So you compute 1/r potential, you solve for the hydrogen atom solutions, and then you add QED corrections to it to get different energy levels here. And then what do we do in the case of getting to get this spectrum for QCD? These are very different approaches as one goes to obtaining a spectrum like this for QCD. And so today's talk will basically try to focus on this spectrum and how do we come across and compute this spectrum. And this also I had spoken about. So where you have QCD spectrum is basically taking the quarks, and these are the different masses of the quarks starting from the lightest to the heaviest. In our calculations, we mostly focus on the light quarks. You can see here the up, down, and the strange, which ranges from 2 MeV to 50 times 2 MeV, around 100. And you have quarks of different colors, and at the end of the day we have to combine these quarks and the gluons in colorless objects, which we call as bound states. And of course, yesterday, as we pointed out, this is slightly outdated, 2008, and there is an update to this which is 2024, and you can see there are these estimates for the eta and eta prime. Also, I don't know whether you can see it clearly or not, but there has been, the reason eta and eta prime are difficult to compute on the lattice is because it involves computation of disconnected diagrams, and until 2008 we really not care about the precision, so we really did not have a very good way to handle disconnected diagrams. Yes.
Before 2008.
Correct.
Before that, early 90s.
Correct.
There was a paper by Garten from IBM. He claimed the entire spectrum.
I see.
It was around, maybe you don't know, maybe you're not born with.
Possible.
But there was one or two papers which were talked about a lot, and then they completely disappeared. So I don't know what was the problem with it.
Weingarten.
These are in the context of QCD inequalities.
Even he gave even masses and all that.
Or upper bounds on masses, did he give?
Yes.
I don't remember.
So this,
I think it's.
I don't know about this work, but I know that he did a lot of, maybe Apollo also, he did a lot of work after the paper of Waffa and Whitson, which he used to derive some, which he used to derive analytically some inequalities that arrive, mass inequalities that arrive.
I see.
I don't know if he was able to leverage that to actually predict
The masses.
It's worth looking into for you.
Sure, sure. Yeah.
Yes.
Yeah, before? What before? Oh, I said before Waffa.
Yeah.
It is experiment, what is the lens?
So these, the black lines that you see, the flat lines, these are experiments, and all the points that you see are from different collaborations using different actions, lattice actions, obtaining the spectra. And yeah.
So what is the error now? 10-15%?
Yeah, so for eta prime, it's 10-15% of course, but if you look at the PDG, eta prime also has a decay width, and of course estimating it in this way is also not the right way of estimating the mass of eta prime. One has to do a full-fledged. Various colors are basically different collaborations with different actions trying to compute the same quantity.
So should
And
eta prime be much heavier or something? I mean, it looks like it's almost the same mass.
1000. Yeah,
So, but
this is the eta.
It's almost comparable to the K prime K0.
Yeah.
So it's
Yeah,
isn't that supposed to
around
be
the same.
I mean, eta prime isn't it like the muon?
No, that's the thing.
That's eta.
Yeah.
Because the QCD anomaly it's higher. Yeah, because of the symmetry breaking that's happening. The U1.
That's what I'm saying. It's not a pseudo-scalar boost, right? That's the
Yeah.
Yes,
No.
yeah,
Because
that's
the
why it's
anomaly.
pushed.
That's why I thought it was much heavier. But it is heavy.
It's heavier compared to this.
But it's almost.
Yeah. Yeah, I mean you can see the error bars on certain objects are very precise on some. For example, these, the pi and the k, they are super precise.
And
Whereas
they use
if you exactly, but if you go to, for example, nucleon, which is a prediction, keeping this fixed, this is still much precise compared to eta or eta prime or say rho.
A lot of other particles, they are doing quite well, except for eta prime.
Correct, because of the huge contribution of disconnected diagrams. That was
So here the things that are fixed are pi, k, and k.
pi, k, and cascade.
Yesterday, like you also
Exactly,
asked.
cascade. Correct.
So why is that? Why is psi chosen? Is there a
So the whole idea is we have to choose something which is which has least finite volume effects and which is precise.
least what effect?
Finite volume effects, I can compute it to very high precision, and also it's not affected by isospin breaking effects. So if I change the up-down quark masses, I should not see a huge change in the cascade in this case. So, but of course, in this case, it's very apparent that we are talking about masses which are in 1000 MeVs, and whereas the quark masses that you are just using are just few MeVs, couple of MeVs. So this already begs the question that how come we are getting, so they don't add up. Of course, sorry, what? Omega is 782. No, phi is 1020. Omega is 782. Omega and rho are pairs, right? Omega is 770 and rho is 770 and omega is 782. That's, you see the form peak here. So this is, I think, 782, and your rho is around here, 770. So phi is what you're talking about is 1020, which is the mostly kk bar. Okay, so also this is something that you are familiar with, where we have the quark interaction governed by the first term, then you have the quark gluon interaction, which is governed by the interaction strength, the G, and then you have the self-coupling. So if I just use this Lagrangian and try to look at the features, for example, if I just look at an experiment where you have a photon interacting with a proton and exciting it, for example, to a delta, and in this experiment, which has, I just took this scattering cross section from PDG, you can see that when the scattering cross section is plotted against the photon energy, you will see this at low energies, you will see these peaks, which are basically the excitations of the proton itself clumping into resonances. In this case, this peak would correspond to a delta resonance, for instance, and then n star and all the other peaks. And one has to be careful, as I'm using it lightly, that peaks are resonances. You will get to know that peaks, resonance is not just peaks. It's not just a simple definition like that. And it's a whole body of work, people working on defining the resonances as such. Because one can have a very broad resonance which might not be defined by a Breit-Wigner. One has to come up with more complicated scattering amplitudes to describe broad peaks. So in this case, in this experiment, so if I just plot the beta function, the running of the interaction, you will see that in this regime where you see these non-trivial structures in the scattering cross section, your coupling is order 1, it's very high, and as you go to higher energies, it basically goes down. So this is the regime that today what I'm going to talk about, and this is the regime where it's non-perturbative, and one can't just expand any observable in alpha to compute the observable in this regime. And that's why we have to be careful how do we compute the hadron spectrum. Now, why do we need to compute the hadron spectrum in the first place? This is a very new motivation. Sorry, what is the? This is the photon energy in log scale. The Q. GeV, yes. So this is basically this photon, how much energy, if you keep scanning it with different energies, what happens? So if I hit the photon with this low energies, I get to excite my proton to a delta, and so the detector that you see a lot of production of n pi states, an excess, which leads to this peak, right? And then it disappears at some point. So that's when you say, okay, this excess is what we call as formation of a resonance or a decaying particle.
So what did you say about the second peak?
Yes, it could be n star 1535. Yeah, there is possibility there. So all these peaks would represent a resonance structure. One needs to disentangle them individually and then look at them. Okay, so now let's go on to the motivation. Why do we need to? As you can see, these non-trivial structures coming up, and in experiments also, these can come up as intermediate states, right? So one very common test that we know of is the quark mixing angle, which is the CKM matrix element, which is a BSM test if I have any deviation from this matrix that you see here. In this matrix, what you see here is basically how the quarks mix among each other. In this case, the VUD is the mixing between the up and the down quark, US up and the strange quark, and these are the processes where you see this happening. So essentially, and the proposal by Kabibo, Kobayashi and Masakawa is this matrix will, to preserve the universality of the weak interaction, this matrix was proposed back in the 60s, and it is a unitary matrix. So what you see here, this VTB one never really measures in experiment because it's super high energy, right? So one can just predict this based on the unitarity condition on this matrix. So in lattice, what people do, how does one go about measuring these mixing angles? Is in experiments you just measure the cross section for each process that you see here, and the process is after that one can write the experiment as a product of a known function, just the phase factors, and then you have the CKM matrix, which is the probability of a certain quark going to another one, so up going to S or U going to B, and then you have the matrix element corresponding to this process. So this is how one relates or computes this particular CKM matrix. Suppose I want CKM, then what experimentalists do is they take the cross section that they measure in experiments and then they have an estimate from pheno or from lattice, the hadronic matrix element, and then from the ratio of these two quantities they get to extract the CKM matrix, the CKM mixing angle. So today's talk, I mean, here what I'm going to emphasize on is this particular VUB process, and it was brought to the notice in the lattice community that if one goes about measuring this is a number from the flag estimate, and what you see here are all the different estimates from using different NF number of flavor of fermions. 2 plus 1 is up down is considered the same, and then you have a strange. So if I go about measuring this process where you have a B meson decaying into a pion and a lepton and a neutrino, this process has a 3 sigma difference from what is measured from inclusive decays of the B meson. So what you see here is an exclusive decay where B is exclusively decaying to a pion, but essentially one can also, instead of exclusive decay, one can look at the inclusive channel, which includes all the processes that it can decay to, and take a sum over them, and then get an estimate from PDG for that. And one can see that there's a discrepancy between the lattice estimates of this particular quantity compared to the inclusive channel. So one proposal that we have recently made in one of our papers. Yeah, sorry?
Yeah, what is the x-axis?
So this is just the value here, the VUB value. You see, this is VUB, mod VUB times 10 to the power 3. So to describe this discrepancy properly, to basically try to find an alternative way, another exclusive channel to compute the same quantity here, we are proposing why not use the rho, because in experiments rho being a resonance will give you an excess of the pions, and this will be a more better estimate in that sense. So what we ended up is
Hadronic matrix element, that means it is the thing that you get from lattice QCD which does not take into account. There is no weak interaction.
there is no weak interaction. This is just the
So basically the pions are all stable.
pions are stable. Correct. Yes. So this is the process that I am talking when the B with the weak. So I'm talking about this matrix element here. So when it gives rise to a rho, which will decay into pi. So this process, and for this process we ended up computing this matrix element, and this was our recent paper in January this year, where we are proposing that this will give you a better estimate for the process for computing the VUB from experiments. So basically experiments like Babar, Bell and Bell 2 have the potential to compute this quantity because they are measuring the rho decay cross section of the B. So this is one proposal that we recently made. And okay, now let's go to the next one, which is I think the golden boy everybody is talking about since last week when the results came out. So basically the G-2 experiment that was that published their results last week, and also the white paper came out last week. So essentially here is where you decompose your A mu standard model. You have a muon which interacts with the photon, and then the spin flips, and this transition is or the helicity flip transition is captured by is what one obtains by measuring the G value here. So once if I compute this G using this experiment here, and then if I want to predict this particular process through our standard model of particle physics, I can actually just take this quantity, and this was first predicted by Schwinger back in 1940s, and it was just alpha over 2 pi, and then people put their heads around and computed up till 5 loops, and this was a 2017 result. They have this muon in the appendix also. Not Schwinger, sorry, this is the muon. Yeah. So yeah, for the Schwinger model, one is just alpha over 2 pi. Exactly. This is one does not need a mass of the muon, because only when you compute this loop, that's when the mass comes into the picture, and then you have to take into account which lepton you're talking about.
Even this loop is giving this.
This loop is not giving, just this point is giving you this alpha over 2 pi, right? And then you start taking.
One loop correction is
This loop is giving alpha over 2 pi.
The first loop uses
Alpha over 2 pi, exactly. This is what Schwinger had computed. And then if you add in more loops here, that's when you get alpha square terms. Yeah, so these are alpha square, sorry, I just mentioned it here. Yeah. Sorry.
No, the anomalous magnetic moment at leading order
Yes.
is independent of the mass. It's universal.
And yesterday flashed up the tombstone of Schwinger where alpha by 2 pi was written.
Yes. He has it on his tombstone as well. Mass of the lepton. Yes.
No, that's the EDM. This is the EDM also.
So you're
The
saying
one loop could be alpha by 2 pi.
Yes.
not
That's what I'm
the
saying.
movement
Yeah.
of the mass. But the magnetic moment itself is always proportional to mass.
Yeah, I mean, this has extra terms, obviously.
This thing
Yeah.
is multiplied overall.
Yeah.
Magnetic moment is always proportional.
This is the gyromagnetic ratio.
So this is a dimensionless number. Yeah. So there is no dimension to this. That's why it's a smoking gun evidence for standard model of particle physics. It's a dimensionless quantity, and it can't be actually tweaked by changing the standard model parameters that you have. So it's basically fixed in some sense. You either get it right or you don't get it right. So we have to get it right if I have to see whether a standard model is correct or not. So since it's a QED process, it has a huge QED contribution, you can see here, which has been computed up till 0.001 parts per million. And then the most uncertainty is given by the HVP part, which has been, which is going to be the topic of my talk today. How do I get this estimate to very high precision? So because of this uncertainty that you see here, there was a huge issue in the lattice estimate itself, which got resolved until very recently. So this is what is the current scenario in the lattice community, or in the G-2 community to be particular. And this is what was announced last week, this red band from experiments, which is basically an average over all these red points you see over here. So this is the first experiment, the BNL, and the Fermilab 3 runs. And so until now, the lattice HVP part was actually huge. And until very recently, this is the white paper which was proposed, which was put on arXiv also last week, which is basically taking a side. You can see very clearly it's taking the side of being close to the experimental value of G-2, and what you see up here is what I'm going to explain in the next slides as to how does one obtain. So these are all experiments that you see here, right? SND, CMD2, Babar, Chloe, Bess, SND20, and CMD3, all, and the tau decay. In these experiments, there is an alternate way which we call as the dispersive estimate, which takes in input of the scattering cross section from this area, which is the R ratio from this experiments that you see here, and then they try to compute this particular quantity. I'll go in details in this slide. Let's look at it in details here. So what you see here is, look at this blob again. So HVP, what do I mean by that? HVP is basically this hadronic blob. So you have this virtual photon which can give rise to all kinds of intermediate states here. Depending upon the energy of the virtual photon, this can give rise to pi states, 3 pi, and so on and so forth. So if I want to go about, so what does this whole expression actually mean? This means that I have a electromagnetic current, and if I am only interested in the hadronic part, I have to take into account the charges of the corresponding quarks that you see here, U, D and S. So this is my electromagnetic current and the corresponding charge of each of the quarks in front of it. So I have to compute the matrix element, which is J mu x and J mu. So I'm creating a quark anti-quark pair current here on the left and destroying it here. So which basically entails to computing this particular quantity, which is known as the HVP integral. And if I just take this integral, so what you see, what we have done is I have taken this whole integral, and one can basically write it, decouple it, say that this part is the QED part, and I can write this as FQ square, and then I can write this blob as the HVP part, and I can put that in the pi q square. And you can see that I'm subtracting a pi 0, which is basically the infrared divergence. So everything is finite, what I'm measuring. And if I just plot the integrand with q square, you will see again it has the huge dominance from the low q square regime, right? So it basically is non-perturbative inherently, the hadronic blob. And in order to compute this for our dispersive approach,
This curve is obtained from, I mean, from where? Is it from experiment or?
so this is from experiment, and you just take this is a well-known function pi q square, and
that's because of which we need to have a prediction that it has to be proper.
correct. So as I know that this particular quantity, the hadronic part, can be computed in two different directions. So this is the one which is the dispersive approach, where you compute a mu HVP. You write, so if I write this particular quantity, okay, let me show, okay. So what one does is write this pi q square in terms of the intermediate states using the optical theorem. So this entails to writing this this current as the mod square of this scattering cross section. So this is basically E plus E minus to hadrons, and this basically includes all the channels that E plus E minus going to a photon and can decay into all possible intermediate states. And this enters into the expression through the R ratio. And this K, the K tilde that you see, or K prime you can say, this is a QED known function. And you can see this S in the denominator, which is the center of mass energy. Again, this signifies that it is highly sensitive to the low parts of the center of mass energy.
What was capital R?
Capital R is the R ratio. Basically this expression. Yeah, that's, and these are all well regular analytical functions.
C minus to everything divided by
C minus to mu plus mu minus.
It's just used for calibration.
Yeah. And another approach that we know is, if I just take this integral, if I can write this as this partially summed over the current correlator computed on the lattice in Euclidean time, which is GT. And so this expression, now if I feed it in here and I compute the Q integral first, I get this K tilde term, and then everything is just a function of T, right? And the T is the current correlator for zero momentum current correlator in the Euclidean time. So this was also proposed in 2011 by Mayer and Bernecker. Of course, this method, you can see that this does not have a direct experimental input. This is non-perturbative because this can be computed on the lattice, and one can actually compute this for different flavor decompositions, from light, strange, charm quarks. And because this is computed on the lattice, we'll see that there is a systematic way to reduce the error in computing this quantity. The dispersive relation approach, why is it so challenging? Because the R ratio that one goes about computing, which is basically the ratio, the sigma hadron over 4 pi alpha square over 3s, this quantity has all these non-trivial structures at low energies, which is the rho, omega, phi, shape psi, and so this is where at low s, this region contributes the most to my integral, and that makes things extremely challenging. And we have someone here who actually did a computation for the A pi pi back in 2020, where they took the rho and the omega, this low energy part, and they actually computed the A mu pi pi using the pi vector form factor. So another thing why is it so challenging is because this particular region has so many channels it can decay to, right? So if I want to measure this in experiment, I have to carefully compute all these different decompositions in all the channels, and if I miss something, I might be off the result. So that makes it extremely challenging, right? So now we'll talk about the lattice methods. So lattice methods, of course, this is again the Euclidean rotated Lagrangian, and we'll talk about the up, down, and the strange quarks mostly here. And what you see when I put these quarks and the gluons on the lattice, what I get is a regulator essentially. As I said yesterday as well, it's a regulator where you have a UV regulator, which is the lattice spacing, and you have an infrared regulator, which is the box size. And then you start off with unphysical quark masses. If you tune your quark mass accordingly, you might reach the physical quark mass, which we have. We'll show you how. Okay, so this is a very simple picture. When you have the Lagrangian here, this is the self-interacting term. This is just given by the plaquettes. And then you have the quark interacting with itself, which is quarks are at the vertices of the lattice. And then you have the quarks interacting with the neighboring quark with the gluon in between. This is the...
Watch the previous one. What was the gauge field part? You had something on the right hand side there.
Oh, this is just this SU3 matrix. Yeah. So every edge has an SU3 matrix, you can think. Right. So how does one go about measuring? So this is a thing that we all see in statistical mechanics, where you have an observable where it's computed. So you have the observable, which is basically a function of the quark propagators, which is the D inverse. This D, script D, is basically this quantity in the brackets here. And there are dynamical fermions which are coming into, which is basically this determinant condition here. So this is what actually changed in the past 20-25 years, because people were doing quenched calculations, which is essentially setting this determinant condition to 1. So I can never form intermediate quark-antiquark pairs when I'm computing anything on the lattice. That means essentially that. But now we have actually overcome this, and we are computing things with dynamical fermions. And what this essentially means is Sorry, yeah.
So, what was so here, your Lagrangian is basically all the things on the top.
Correct.
And so, what is this quench thing that you're doing?
So this term that you see here, the determinant term. So what I can do is, I think,
is it like, so that why is?
I think there is this L that you see here is basically the gauge term only. And this is, you can convert it into yeah. So basically I'm integrating out the fermions in some sense. I'm writing them as determinants. So how does one go about computing this quantity is, so if I want to compute this integral, and if I don't know the partition function here, the most common approach to compute this infinite dimensional integral is using Markov chain Monte Carlo. So I'm producing gauge field configurations. Basically it's a set of SU3 matrices in the box that I generate using a probability which is given by this blue, right? And I'm using importance sampling, so I'm not sampling over all the possible U's, but only the ones which has the highest probabilities here. So I'm generating such boxes and storing them with me so that I can, next time I measure something, I can just compute on these boxes that I have already sampled, and I can get whatever quantity I want to measure, right? So, and because these boxes are humongous, and this has to be stored in supercomputers, you can see here, or on huge storage systems that we have available. And then you can see that observable can also depend upon the quark propagators themselves. And quark propagators essentially means that I have to compute and invert a matrix, the D inverse, for this whole lattice size that I'm talking about. A typical lattice size is, for instance, 64 cube 192. So I have 64 cube 192 lattice points, and each point I can have a quark, and the gluons are distributed over this whole lattice volume. And of course, because of this, you can see the D matrix had the mass term in it, right? And that's where the problem starts to happen, because my D inverse will be inversely proportional to the mass of the quarks, correct? And inverting such a huge matrix makes it ill-conditioned, and that's why it was computationally intractable up till now, actually, up till maybe so this was 2010, last 15 years. We have made a progress in computational domain to invert matrices which are extremely ill-conditioned. And what does that mean?
Ill-conditioned because the M is very small.
Exactly. Yeah, so the eigenvalues are very small. So I can't, if I try to do D inverse directly, I'll get gibberish. Huh?
You get huge numbers.
Exactly. Basically, I'll get out of my machine precision that I can see, I can store my computer. So I have to really I have to come up with smart methods to deal with this low eigenvalue things. And this is not just lattice QCD. Such issues happen in all fields, right? We come across computing this low eigenmodes, the eigenvalues which are extremely small. How do I invert a matrix, such a matrix? This is a very common computational problem in all domains. And so this is an idea which is, I think, also partly borrowed from hydro people and computational people, where this is called multi-grid approach. Where you see here is, if I just write my matrix which has all the different modes as this complicated function, and what I do is I want to smoothen it out because it's very complicated, and I am only interested in so this has low modes as well as high modes, right? And for high modes I can easily invert. High modes means high eigenvalues, low modes means low eigenvalues. So high modes I can invert, but low modes I can't. So what will I do? I'll first split my matrix into two components, high and low. And then what they do is, so this is the trick here. So if I have a huge lattice, this is also an idea from RG, where you have a huge lattice, I make domain decompositions. I make a small domain. I split my lattice into small domains, right? And then because in the small domain, I will have only the low modes that I am trying to solve. So what I do is I first take small modes here. I make them into small boxes. I smoothen it out. Basically, I solve the system in these small boxes instead of the whole box together. I make it's called finer grid and coarse grid. There are two grids I'm splitting my whole box into, right? The final grid is the fine grid that I want my result in, and then I coarsen it to a small box. And the coarse grid, I solve my system because it is a small box. I can get a solution of the system, and then I will project it back to the big. So that is what is happening here. I'm computing my approximate solution in my coarse grid, and then I'm projecting it back to get the final solution. So this is basically done in steps. And the more issues you have, the more coarser you can go. You can have multiple levels in the multi-grid. Exactly. It's just in different language. And the beauty of this method is, you see this red line, so this is basically the seconds to solve, like how fast can I get to a solution, and this is the quark mass, the bare quark mass that goes into the D. And you can see if I use my regular approach, which is basically a bi-CG stab, which is a conjugate gradient operation, stabilized conjugate gradient operation, and this basically makes it extremely difficult if I decrease my quark masses, right? It makes the time blow up if I reduce my quark mass. But if I do this multigrid approach, which is a mixed precision multigrid approach, you'll see almost no dependence on the quark mass, because this makes things much more tractable for physical quark mass calculations. I can actually compute things using physical quark mass because of this advanced algorithm, which is taking care of getting a solution using physical quark masses.
These machines are what?
So these are the machines in US, the Corey and Edison supercomputers, and so these are of the, I think
They belong to whom?
they belong to, I think, the US government if you log into them. So this one is actually in Munich, this is German, and this is also German, and these are US made machines.
And these, which company is making them, or they are custom made for purposes of physics? Or?
Well, these things I think are made by Intel, because it has Intel processors.
So you actually use these computers?
Yes.
And how do you, what's the mechanism by which you...
So the idea is you write proposals, you propose a problem, so they are open for academic.
It's for civilian use.
Correct. So what you do as academicians is you write proposals saying that I want to perform this calculation, this is my code, and this is how it scales. If I tell them I'm getting such a big speed up with such small resources, they will be very happy. They are, because it's important that we do things efficiently. We can't be inefficient in what we propose, because we're competing against all the different people from...
Which collaboration?
I'm a member of several collaborations actually. People. So there are interesting things about the machines themselves, because since my PhD was in computational physics, we had to make a report on supercomputers that exist all over the world. The smart thing about this computer in Munich, the next time you visit Munich, you should remember that airport has a supercomputer in it, in the basement.
The airport?
Has a supercomputer in it, in the basement.
Oh, this one.
Yeah, this one. And the airport is kept warm by the computer. Exactly. The more computations you run, the airport is getting the benefit of it in the winter months. It's in Munich. Yes.
And the lattice you are drawing here, I mean, it's like, half the part is very noisy, half the part is like...
So you split your lattice in two modes, the low modes and the high modes.
It's D inverse, right?
Huh?
It's the D inverse matrix.
No, this is not the D inverse right now. This is the D matrix itself before inverting, because if I just invert D, I can't do it because of this low modes here.
First you smooth.
So first I do is I take the smooth part in the sense, okay, I should be very careful here. The smooth part are the low modes, which is the one that's causing the problem, right? The smooth low modes means what? Which are changing very slowly. They are very slowly changing. So basically this, they are changing very slowly, and the one that changes very fast, right? And the eigenvalues determine that. If the eigenvalue is small, then they are changing very slowly. If the eigenvalue is huge, then they are contributing to high mode fluctuations. And the problem that is caused by are the low modes, which are the smooth parts here. So I have to take this and then I have to coarsen the grid and solve it. So essentially I'm trying to construct a preconditioner, they call it in computational domain, is a preconditioner which is essentially an approximate solution to the actual solution, and then I use that. And in some contexts they are also calling it as a machine learning example back in 2011 in the Lattice community, because this approximate solution is obtained by exactly, yeah. So this is what one can think of it as one of very early applications of machine learning as well. Okay, so once you have the propagators, yeah.
So you stop long wavelength modes and short wavelength modes, but
Yes.
presumably there are modes intermediate.
Correct.
Modes also.
Correct. There are.
So how do you?
But the intermediate modes are something we can handle, and the long and the high wavelength modes. Okay, high wavelength means low frequency.
High frequency.
Yeah.
modes.
Yes.
So there are low frequency modes which you have drawn as a somewhat smooth surface.
Yes.
The high frequency modes as a jagged ones.
Correct.
But imagine that there are also modes in the
Intermediate. Yeah, those things I can solve. So things which I can solve, I keep it. The things which I can't solve, I approximate a solution for it. And because this is a huge box, I can't approximate a solution in this huge box. So I go to a coarser grid where I only have the low modes.
So by solution you mean you can find a D in the
Approximate D inverse.
The question is finding the D inverse.
Correct.
By solution you mean you find an approximate D.
Correct. Correct.
And this D basically, I think for this, what you're saying, it seems to me that it is kind of important that the derivative operator is kind of linear, isn't it? Is
The derivative operator is linear. Yes.
Because otherwise it seems to me that it will be coupling between the relations. The modes that you're trying to solve,
Yes.
which are high frequency
Yeah.
versus low frequency.
Yes.
So you have effectively that D is such that it has decoupled the frequency.
Yes, you can decouple into high and low as well.
Yeah.
Then you can take it out. Doublers is how you discretize your D, right? That will tell you whether doublers are existing or not. I can always choose a discretization scheme, which is Wilson Clover fermion. Wilson fermions won't have the doubler problem that you, but then you always trade off, right? You get rid of doublers, but then you have chiral symmetry explicitly broken. So then you have to say that, okay, for the time being, we'll keep it like this, and then as we go to the continuum, it should give the same number, same result that we expect. Yeah, and there are different ways, domain wall fermions, where you have, where you basically you have chiral fermions there, but you don't have, you also have, you push the doubler modes into another dimension, the fifth dimension. Yeah, so for this calculation that I'm going to show you today, we are using Wilson fermions, so there is no need to worry about doublers.
So in this method, you are just using your final function is going to be Weberian and smooth. I mean, okay, some Weberian function and not spectra. That's what you are using.
For?
I mean, in this method, the method of smoothing and.
Oh, yes. So we are not actually smearing it as such with some smooth kernels. We are taking the D and we are trying to find the inverse of it at the moment.
It's the part where you kind of solve.
Yes.
That part is approximated by continuity.
By projecting it. So I'm saying that, of course, for the whole lattice I can't solve it. So I am taking an average of these 4 lattices into one. I'm coarsening the whole lattice. So if I have this, suppose if I have a grid, so let me just draw it, that would be easier. So in 2 dimensions you can think I can take, if I say I coarsen it, this is a 4x4 lattice, I can coarsen this box into one point, just take this point, and then from this box I take this point, and from this I take this and this. So I basically have a 2x2 coarse grid. I solve it here and then I project it back, approximate solution to this 4x4. Now this solution is more closer to the actual solution than if I start with inverting this one directly.
These 4 points are like some low.
No, this is our actual lattice. There is no this is the coarsen points here. Yes. So if you have bigger and bigger lattices, you can go further and further in these grids. Okay. So once you have this D inverse, which is essentially some inverted matrices. Yes.
It only works for the lattice case, or it works for any matrix?
It works for, essentially, it has been shown that it works for, this is an idea not from lattice, it came from people who are doing hydro. So where they have this low modes and high modes issue, and they can actually separate the low modes. And so it's, this problem itself is not restricted to lattice, or this solution that we have multigrid. This is a very well established solution in the community of computational folks. Yeah, we are just leveraging.
Varying so slowly, and if you have too much grid, you are retaining too much information.
Yes, and we don't want that much information.
Is
Galerkin, Krylov, this is basically, this kind of solvers are called Krylov solvers, and these are called Galerkin scheme. How to,
the hydro feature is those.
yes, yes. So there is an overlap of nomenclature between, so we have to keep borrowing ideas back and forth. You will see that certain ideas from lattice have actually become a part and parcel of the common world now, which is gone by the name of hybrid Monte Carlo, HMC, because it was first proposed in lattice in the 1980s by Tony Kennedy in Edinburgh. So he works in lattice, and now that particular approach, the hybrid Monte Carlo, has penetrated in all the different fields by the name of Hamiltonian Monte Carlo, which is essentially some kind of integration preserving steps you do while doing Markov chain Monte Carlo. Volume preserving, yes. So you have conjugate momenta where you evolve your systems in locally while preserving the Hamiltonian of the system. Okay, so now you take this D inverse, which are basically matrix inverses, and then you compute the matrix products, which is the contractions, as you have a point source where you create a particle in this lattice at some point, and then you take all possible paths it can take from this to all the paths in the whole lattice, and that's the D inverse. And once you compute this propagator, which is product of these T propagators here, you get, and then you take all the traces of color and spin contractions, you finally end up in a colorless object, which is computed for each lattice gauge configuration that you have, which is O, mu, n.
This seems like conventional lattice. Like, where did your Lucier thing go?
Not yet, not yet. So this is a very conventional, which has been followed from the time of Wilson, which was first proposed, and people have been computing back then. And as the computation power is increasing, they're computing more and bigger boxes. And so this whole setup is then repeated. Yes. And this whole setup is then repeated with bigger boxes, finer grids, and smaller quark mass.
And this procedure that you described is called quenched.
This is not quenched. Quenched is when you set this determinant to equal to 1. Yes. So basically you are not allowing for any quark antiquarks to form in between this. Right? This is just plain band. So when I say it can form quark antiquark, when you do the integral, the path integral, it can produce dynamical fermions while. So if I set this to 1, then I don't have that, and then I get an incorrect result.
So compared to the 2008 or something, what is the improvement here?
Well, the improvement is, of course, a better strategy to handle the disconnected pieces. You have eta and eta prime. Yes.
Yeah, sure. I mean, that is not like, but I was just, what I'm saying, the technology, the eta prime is not more like output. I'm saying, like, what was in this calculation, what was what was improved in the strategy? Partly probably this 1/m cubing.
Exactly, the multigrid. So previously people were using this solution, but now they are more agnostic to quark masses, so they can be more faster and efficient in computing this.
And I think that directly helps you in going to the physical quark.
Correct. So this is a typical computation that we have a 2-point function, have a creation operator, destruction operator for a correlator with momenta p, and essentially you insert, this is the continuum operator, you insert a pair of states, lattice tower of states, which has the same quantum number as which has the same quantum number as the O dagger here, the operator, and then you essentially get a sum of exponentials, and the one that survives is the one that decays the slowest, and that becomes the mass, or in this case if is the momenta p particle, and all the higher momenta states are suppressed. So this is the log plot that one obtains if I just do a calculation of such. This is, for example, the pion computed with different quark masses here. So as you see, these are very good for isolating single hadronic states, and the ground state survives. But I guess because most hadrons are excitations, this method fails, and that's why we have to come up with using multi-hadrons.
So this is the correlate, I guess.
Correct. This is just the log scale.
How is that connected to this?
So this, just you fit it, get the mass, and then you write it here. This is a very simple approach, tried and tested for last decades.
We know what the decay should be.
Correct. Okay. Now we talk about excited states where you have multi-hadrons, right? You have, for example, you look at rho, it has pi, you have delta, you have n pi. So you have this multi-hadronic states, and you have to combine them in such a way that they form the same quantum number as the target hadron that we want to study. So how do I do that? Two hadrons on this lattice, they have to have a relative momenta between them, right? To finally give the target quantum numbers that we want between the two particles on the lattice. But on the lattice, I have a restriction. I can't move freely on the lattice. There are only restricted symmetries that I have on the box. And that's why you really, you don't have all the nice properties of the continuum spin that you want to study on the lattice for the two hadron operators. So the orbital angular momentum between these two particles are constrained because of them being on the lattice. So I really can't construct any possible spin state taking these two particles. I have to come up with a strategy to map the symmetries of the lattice to the continuum. Technical limitation, correct. The lattice itself is giving you that limitation.
What I mean is, trying to ask is that it is not coming from some conceptual argument. It is coming from the way that the system of the two hadron operators on the lattice.
Yes. I mean, on the lattice, you will always have this problem. No matter.
It's conceptual, the way, why, framework, lattice framework.
So, if I choose some other framework, then I don't have that. I agree. Lattice is giving you this. Yeah, it's technical to lattice. Correct. That's the point. So we have to come up with strategy to map the orbital angular momentum from the continuum to the discrete rotations that we have on the lattice. Right? So this is what we call as the subduction method, where you have all the irreps. So you need kind of group theory to map the continuum irreps into the discrete irreps on the lattice. So this is the orthogonal group on the lattice. So you need to construct these projection operators to project the continuum to discrete. And then what you do after projecting them, you have the single hadronic states and multi-hadronic states. Then you do a variational principle, and then you obtain the eigenvalues. So scattering states on the lattice, as I also mentioned yesterday, it was a problem because one can't really extract this resonances directly on the lattice, which is why people had always had issues computing dynamical quantities like resonance decay widths and resonance masses on the lattice, because this scattering continuum is not accessible on the lattice. And this, as we saw yesterday, using Lucius method, we can actually access this continuum and get the masses and the widths. And of course, the only two things we need, as we said, in unitarity and locality of my range of interaction that we have. So what does unitarity mean? Which means that I need to know all the elastic channels that my particular particle can decay to. If I miss something, I can't apply Lucier formalism in that case. I have to make sure that I am considering elastic scattering only, which means I'm considering all the possible channels my particular resonance can decay to. And this is the mapping that we discussed yesterday. And this is a very, very powerful approach, and one can just marvel at what all things one can achieve. So what I discussed right now is, if I get the spectrum from the lattice, which encodes the information, if I use Lucier condition, I get the scattering phase shifts, right? But essentially, suppose I want to do a lattice calculation about certain resonance, X resonance, right? And I know that it exists in experiments. I know it has a phase shift curve. What I can do is, I can do an inverse Lucier, right? Suppose I have a configurations which in my computer, and then I want to perform this calculation. What do I need to know? How should my spectrum look like? So I can do a back of the envelope calculation beforehand from experiments, right? I can take the phase shift, feed it in, feed the lattice spacing that I have in my computer stored, and then I get the spectrum that I expect given this resonance that I want to study. So I can do a thing that I can do a inverse Lucier calculation beforehand, before actually going into the lattice calculation. I can do this and get an estimate of what should I expect in my spectrum on the lattice. So this is, in that sense, essentially a very powerful approach. I can use it either ways, from finite volume to infinite volume, and the other way as well. Okay, so this is the calculation. No, I don't have to know. I just need to know the scattering, resonance, the phase shifts. This is published from the experiment, right? Yeah.
You never know whether it's really exhaustive. I mean, even if you took something like a blue ball about which people argue forever,
Yes.
these things keep mixing and you don't know what are the final states. Especially when you go higher up in energies, as you mentioned, there's so many final states.
Yes. So that's why we are mostly interested in the low-lying states, where the decay channels haven't opened up yet.
Is it really necessary to know all the elastic states to which
To apply the Lucier condition,
no, but that is
Well, there must be some truncation somewhere. So how sensitive is it to that kind of a truncation?
what do you mean?
I mean,
Let me see.
because your states are small.
Hmm.
I mean, you may have virtual particles
Yes.
in the strong energy spectrum, not BSN physics or anything.
Yeah.
That were never really experimentally proven or disproven.
But we have this branching ratio that we know from experiments. So some channels, I know it decays to 99%.
So when you say
No,
decay,
that's
that's
what-
only through QCD. Or
Yeah, through strong
So
interaction.
which means that once you have a spectrum like state at some level, there's only a finite number of
States that it can, decay to. Exactly. So it's the bottom going up.
But we really don't know. So my question
I
is,
see.
if you truncate something like this,
Yes.
how sensitive is it? I just want to know the robustness of this.
How sensitive to inelastic channels that can open up.
Exactly.
Yes.
Yeah, for instance, if you take two protons and scatter them
Yes.
very, very hard at each other,
Hmm.
then I mean, a few weeks ago people came and told us that we will form UGP. which
Yes.
is an hadron.
Yes.
Right?
Yes.
So I suppose that is a kind of situation that may have in mind, or I have in mind. That happens at very high energy and will produce just from
Intermediate
will
states.
produce hundreds of other guys.
Yes. So that's why. So this is
But,
that's why.
But on the other hand, there may be a sensible way of are saying that I'm not going to be looking at such high energy scattering of two protons.
Okay.
I'm only looking at, there may be a sensible way of saying I want to look at only low energy scattering of two protons.
The answer to that would be like there are two approaches. This is an exclusive approach where you know the exclusive channels the thing can decay to, and you are computing the scattering cross section for those channels. And the thing that you are saying is in an inclusive approach where it can decay to any number of things, and I want the whole information out of it. And there has been a recent approach which I am gonna talk about probably in a couple of months when I come here in October. It's called spectral function. So the Euclidean correlator that you see here has the information of all the channels that it can decay to, right? But it's our choice that we are looking at only the lowest energies of the Euclidean correlator. But it has the information of all the correlators that it can decay to. So the technique that we say is that we can take the Euclidean correlator and do an inverse Laplace transform. That will give you the information about all the possible channels that it can decay to. So that's what we call the inclusive approach, where it includes all the possible channels, which involves solving an inverse problem, which is inverse Laplace transform of your Euclidean correlators that you have. So that's an approach. I'll reserve it, but we can discuss more about it. Right now, this is a exclusive approach where I know the decay channels and I'm on to nail down my resonances and study the properties of resonances. Okay, so this is the calculation that I'm going to talk about, where we have a box of 96Q192, a 6.2 Fermi box. I have a physical pi and mass. I have these many configurations from our Monte Carlo simulation. And why do I choose?
Like spatial dimension and time dimension, there are different lattice sites.
The sites are different, but it's the A itself is zero temperature.
What is the idea of using more and more
Time slices, because I want to go to the ground state, right? The one that survives, which if I do an exponential decay calculation, right? If I have all the excitations in the beginning of the exponential, I don't want them. I want that survives, the one that survives, the mode that decays the slowest in the exponential decay, right? And for that, the bigger the time slice I have, the better it is for me that I can actually fit things, correct? If I have a smaller time extent, it makes me difficult to figure out things, how much should I fit? Maybe there are 2 exponentials, maybe there are 3 exponentials, which is again an ill-posed problem. Fitting exponentials is again an ill-posed problem, and it's a problem not just faced by lattice people. There are people right down the corridor, NMR people, having the same problem of fitting multi-exponentials. So it's something that we all are dealing with. Yeah. So you have this periodic box here, 96Q192, and then you construct operators, pi operators, and you scatter them off elastically, because pi is elastic from experiments we know up till 1 GeV. So the 4 pi operators don't really contribute up till 1 GeV. So the process is we construct the single hadron operators. This is the meson operator, where you have the psi bar, psi, which is the quark, anti-quark, and then you have the gamma 5 for the pion. So this is my meson operator. And then I construct QQ bar, which is meson rho like operators, and this pi operators. So basically take 2 mesons and then construct multi-hadron operators. And you can see here I smear them, right? Smear the operators themselves. So what do I mean by smearing? This is a very interesting technique where you have the psi fields, but then when I create the psi fields in the space-time, I need to figure out a way that I can automatically remove the excited states right from the psi fields itself, the way I define it. How do I do that? So there is something called a smearing kernel that is put on front of the psi fields. It's multiplied with the psi field, which is in some sense trying to isolate only the low modes, right? And if I can do this particular step in a gauge covariant way, then I am done. And this is what a typical idea looks like. So if you have the original Xi field given here, what one does is I can decompose this in the Fourier domain. Again, the low and the high picture comes to your help. So all this, you see this, there is a low mode, lot of low modes and lot of high modes in this gray band. And then I just truncate. I remove all the high modes. And then I reconstruct it back. So I still have the more or less the same feature of the fields which I want, but I got rid of all the high modes or the high frequency excitations that I don't want. So this is what is essentially happening by this S field here. And this was also put forth in 2011 and 2009 by people like Mike Pearden and Colin Morningstar, where they have shown that this smearing kernel is essentially the eigenvalues of or eigenvectors of the 3D Laplacian operator, the gauge covariant Laplacian operator, where you have the Laplacian with the U fields in it. If you use that, the eigenvectors of this gauge covariant 3D Laplacian, and I use that as smearing operator, then I basically get this. So this is essentially showing the radius of the smearing radial distribution. And as I increase the number of eigenvectors, I can see more and more, you see it's getting more and more sharper. I start off with a very sigma. Yeah, sigma is something that you tune. This is basically the cutoff. How many? Yes, it's a number. It's a number. Yes, that's a number that you tune. And this is the theta function, the Heath side theta function. So it's basically truncating. This is the eigenvector of the Laplacian operator, and this is the number I want. So it's cutting off all the other modes and telling you I just want these many modes and give me the smearing operator for these many modes. It gives me the smearing kernel, and then if I just plot with the number of eigenvectors, you will see this. And see, this is being performed at every space-time lattice that you have, that you're creating your quark in. This is the xy coordinates. So if I isolate, so this particular step is very important to get the ground state to very high accuracy. It's very important in lattice calculations. Yes?
Why there are 2-3 points nearby one lattice?
2-3 points because they are computed at different lattices of the same, from the ensemble, if I compute it. So this is not a full-fledged lattice calculation. This is just to see how my spatial distribution looks like, right? So I can do this calculation for several set of like 5 or 10 ensembles to see whether I get the same ballpark. I get a very nice looking distribution. So this calculation does not have an error bar, you see, because this is not coming from a Monte Carlo estimate. This is not done over all the configurations. But I take a subset and I tune, because I want to tune this sigma s, right? This sigma s tuning is done by calculating it over a small set of configurations and then trying to see this plot whether it looks sensible or not. So this is an intermediate step that is performed to tune the sigma s to a sensible number. I think we are mostly done. This is the results. Yes. I don't have the time with me, but
How convenient.
I'm sorry.
No, he asked a lot of questions. That's true.
Yeah. So I'll just go through quickly. Most of steps you know. Most of steps you know, that construction, then these are the contractions that you have to perform. And this is the spectrum that we obtain on the lattice. So these are all the intermediate steps that we have to go through, and these are all the thresholds that open up. And this is the step that I showed you yesterday as well. This is the lattice calculation, the blue points, and then the orange and the lighter blue points are the one from experiments. And you can see that we are right on top of the experimental phase shift curve. And these are the resonance parameters obtained.
So this is integrated to smearing.
Yeah.
The Lewis formula.
Yes. Everything has to be, taken care of and implemented.
And where was the quark mass dependence?
So this is done at physical quark mass. So I have a calculation for unphysical quark mass also. I can show.
Is there any understanding why those
Oh, this.
uncertain? See, there the PET value
Yes.
here.
Yes.
23 is in the decimal place.
Yes.
Whereas
And this is. Yeah, of course, because of this large error bars that you see here.
But
So.
what is the hope in reducing this?
If you see the number of configurations I used in my calculation,
96.
it's 505 configurations only. And people can actually do this for 10,000 configurations. And you can see an order 1 over square root of n scaling of error. So this will go down by almost 1 over, factor of 4. You can see this errors will also go down accordingly. Sorry. Yeah, I'll show that plot as well.
But what will you do? The central value migrates far away from the physical. I mean, it's one thing that the error will shrink.
Yes.
What about the central value? What if it moves out, moves away?
Well, that's as long as it's consistent.
Yeah.
I see.
Let us assume
Hmm.
that you had an error of just 6 MeV.
Yes.
But your central value is say 760. Then what? Do we contradict
Then one of the
nature?
3 steps has to be checked.
Yes, because and not just that, also the lattice spacing. Right now, the Lucier condition is.
My question is more about whether this kind of thing actually converges to the true physical value or not. There's no proof that it will actually converge to the physical world, right?
I see. So there is an a square.
The computer is wrong, and that means the computer is wrong.
So it means we haven't taken into account the a square f or lattice. So right now there are 2 systematics in this. Because it's lattice, we know the systematics very well. And that is the lattice spacing, and the quark mass is taken care of already, and this is the infinite volume quantity. So the only systematic in this calculation is the lattice spacing. So if I have somehow messed up how I discretize my lattice, if I somehow messed up how I define my derivative operator, that will be the cause of issue.
What I'm saying is there is no proof that the lattice itself in the continuum limit will actually be the physical world. I mean, mathematically it has not been proved. So the reason, of course, my interest is from the G minus 2.
Yes.
Just because the lattice is agreeing with the Fermilab experiment.
Yeah, that is.
And it disagrees with the real, what I consider as a real world, which is the
Dispersive approach.
Is there a 70-page proof by Karim Badaksh in Farafan?
I don't know, is there?
There is no lattice as a continuum.
Okay. But then it had better converge to the
Yeah,
physical
it's
world.
good saying it.
Okay, very good.
It's a communications of mathematical physics paper. So, I mean, I have never looked at it.
Send me-
I've
send me the
people like
reference.
Polchinski coding it.
Yes.
I see. I'll also look into it. I think as far as convergence theorems, there
There could be a catch because it could be pure Yang-Mills. I think that, there have been modeling, this is an old result.
I think there are Osterwalder has a convergence proof also.
But that might be older than this, I think, and probably not for Yang-Mills.
Yeah, that is for.
That is probably more like.
But they have done it for dynamical fermions, where you have, because Yang-Mills is just you have gauge fields, you don't have fermions, but you need to prove something
There
with.
are several steps that you do which are fundamentally approximations. The multigrade that you did, there
Yes.
may be a problem, there may be a theoretical issue in which how you convert the D inverse.
No, but then you can always check it with your residual calculation, right?
But-
Like
But
I can do a D times D inverse.
that might not be an allowed step in as far as modeling real-world QCD is concerned. Then you'll smear your fermion operator by this aging variant S.
Yes. That's that's not an approximation, right? That's just to make my life on the computation side easier. The physics is the same.
Yeah, but real-world QCD is not about making your life easier, right?
Yeah. I'm saying, so I know my lattice method is first principles, is non-perturbative, but the way I compute it, I can always have some freedom there. For example, this D inverse you're talking about, I can always multiply D matrix with the D inverse to check how close it is to identity operator, right? I can also do a, what was the other one you said?
The smearing.
Smearing. Smearing has to be again gauge covariant. That is very important. And recently, it has been shown that smearing that we do is very similar to gradient flow that you have in Young-Mills. That you just take the gauge fields, right, and you remove the high modes of the gauge fields, and this is basically doing an RG flow, right? Gradient flow. You're on the RG scale, same RG scale as the QCD. So if my gradient flow and my smearing are giving the same result, then I'm sure that at least I'm on the same trajectory as the QCD is on the RG flow trajectory. So that is also a very important information that we need to take into account. Okay, now let's quickly come to the results of the AMU HPP. Of course, as you said that this is the integral that we are computing here, the AMU HPP integral, which we compute we need to get the integrand to very high precision, and these are the error bars that we have to deal with, and that's what is causing huge uncertainty in the lattice calculation. And what me and my team back in Mainz we have done is they have already, the UK QCD people have shown that we can decompose this integral into 3 components, because lattice have different systematics in different parts of the lattice. So the earlier part of this calculation, the 0 to around 0.5, 0.7 Fermi, this particular integral is affected by only the UV part, which is the discretization issues. And then you have intermediate part, and then you have the finite volume issues. And what today I'm going to talk about is this long distance window. And because I know pions are the lowest, the Compton wavelength of the pions are the longest because of being the smallest mass particles on the lattice. That's why they will always appear in the tails of all the observables that we compute on the lattice. And basically I can reconstruct the tail using just the pi states, pions. And that's what we are essentially doing here. We are reconstructing the tail with the pions, make sure that they have the same quantum numbers as this particular current operator, which means I need pi states to create a I equal to 1 current. So I'm constructing this overlap between the current and the pi states. So I again compute this along with this, the current and the pi states. And you can see a very nice overlap of the tail isolating as I increase the number of pi states in my calculation. And the first blue line that you see is obtained from low mode averaging, which is LMA, which is taking into account all the possible modes in the calculation. Okay, so this is basically an exponential reduction in the noise in the tail, and this has led to shrinking error bars. You can see here. This is our result from the Mainz estimate, and these are our collaboration people, and this is me up here. And this is my collaboration. We worked together to get these 3 papers for 3 different windows out, and I had significant contribution in the long distance and the intermediate distance. Okay, so what we did lattice calculation of the AMU HPP and get an independent prediction from lattice calculations. One thing that needs to be done, the next step would be from the phase shift, is to get the form factor and then use that to compute the pion charge radius, which also Narayan has done for the pion charge radius using the form factor very recently. There's a very nice PRL. Yes. And also the pi states, as I say, it comes also in the B decays and D decays. And the same setup that we did here can be used directly for B decays. Also in my process of research, we have also done delta resonance using physical quark masses. And there are new tools like control variates which are being developed for reducing the error further. Okay, so these are my collaborations that I'm part of. This is my PhD collaboration, ETMC Cyprus and LHPC USA, and then this is my postdoc collaborations in mines. Apart from this, let's look at the future research that we can actually do with all these setups that we have. We can actually try to think of how to, so right now this all setup was zero temperature, right? How does this affect our finite temperature? How do the resonances, can we obtain them? So one approach that I would like to explore and understand better is, like yesterday I mentioned that Lucier condition is basically asymptotic Bethe-Ansatz. But there exists also something called thermodynamic Bethe-Ansatz, which includes finite temperature correlators.
What is the first Bethe-Ansatz?
This is, that's the Lucier.
Yeah. And the other one
Is the thermodynamic Bethe-Ansatz that includes for finite temperature correlators. I want to know how one can make a transition from asymptotic to thermodynamic Bethe-Ansatz. This is quite interesting, which I like to understand.
This is, I thought like the Bethe-Ansatz were only for integrable systems. So here it seems like you're applying it for like very highly nonlinear.
That is true. That is true. But given that if the Lucier form can be, if I can look at, for example, when I look at a particular set, say elastic scattering only, then I can approximate that much as an effective field theory of just integrable systems, because I know all the states in this regime, right?
Well, I mean,
If I don't want to look at higher excitations, if I just set a smaller, my window of my Hamiltonian, I truncate it. I don't want to go to higher excited states. I only want to look at the low pi states, for instance.
even if you're looking at the low-lying part of the spectrum, the theory is maybe there's a way, but
I want to know if there is a way, something that I'd like to explore. Okay, so these are my different methods that I really want to explore. So this was a G-2 with the mines people. I'm looking into 3-body resonances as well for the omega-like particles. And there is also things like tetraquark objects, which I'm also investigating. And then these are some novel methods that I'm also part of. These are machine learning tools like alternative to Markov chain Monte Carlo. Also, you will get to hear about it in a couple of months in the tutorial, I hope. Normalizing flows. And also in the framework development, for instance, scattering itself is a very interesting topic even for the quantum computing people, right? People are trying to study scattering of mesons in Ising model framework in quantum computers, because we can model Ising model on quantum computers very efficiently. We can construct a meson-like operator in Ising model and try to scatter them off and see the excitations. And there also we can use, I can study the evolution of entanglement entropy as one performs this scattering calculation. So this is an interesting framework. Apart from this, I had some mentoring experience. So recently I got a paper out with 2 undergraduates working with me in Maryland, working on Monte Carlo methods for variational Monte Carlo for getting the ground state of particles. Then we had a summer student back in Cyprus when I was a grad student. He went on to doing pi scattering with staggered fermions for his PhD with the group in Fermilab. That's it. Thank you.
That's it. That's a lot.
Thank you. Thank you.
Yeah.
Any more questions? It's been
Sorry, it was excruciatingly long. I hope you got something out of it. Yeah.
so if there are no more questions, let's thank Srijit again.